Hi again. Here on your screen, you see this preliminary version of the disk embedding theorem that we've already talked about. The precise text is there, but let me remind you what the statement says using these pictures on the right. We started off with a smooth, simply connected four-manifold M, and here I have a proper immersion of a disk F, which is given here in green. And then this immersed disk, it comes with a partner, which is shown here in purple. This is what I called an algebraically dual sphere for F. What I know is that the intersections between F and G are algebraically 1. So these extra intersections can be paired up plus or minus. The self-intersections of G are also algebraically canceling, meaning that they can all be paired up plus or minus. And then lastly, this immersed sphere G of S2, has trivial normal bundle. And in this situation, what Friedman told us based on constructions of Casson is that I can actually replace my F by an embedding F bar. It's the same as F on the boundary, even including some framing information. And then it's a flat embedding, not necessarily a smooth one. So my goal in this short video is to give you an extremely broad outline of the proof of this preliminary version of the disk embedding theorem. There will not be very many details here. All I'm hoping to explain to you here is really the big broad picture. The details of the proof are beyond the scope of this lecture course. I'll add some precise references in the typed lecture notes. All right, so what is the outline of this proof? It has two broad steps. Here's the hypothesis of the theorem on the top left there. The first step of the proof is constructive. This is the part that's essentially due to Casson and his lectures in the 1970s. So what this step does is it builds a replacement for F. So I'm thinking of F as a thickened version of this immersion. So it's something that comes with a neighborhood. And I replace it with a four-dimensional object called a skyscraper, with whose boundary, especially the portion where it's attached to boundary M, is the same as that for F. And I'll say a little bit more about what a skyscraper is, but not with very many details soon. But it's some four-dimensional object that's morally meant to be an approximation of a disk. And this construction side of things is pretty explicit, it's pretty hands-on, and you'll get a sense of that in a second. The second step is the detection step. This is Friedman's big insight. Friedman came along and he looked at these constructions of Casson and he said, actually, the skyscraper, this, this approximation of a disk is in fact actually a disk. So every skyscraper is homeomorphic to a two-handle D2 cross D2, and it also behaves very nicely on the boundary. So on the boundary, especially the attaching region, boundary D2 cross D2, you can fix prescribed homeomorphism. And then what that tells me is that this middle picture is actually secretly a picture of a thickened disk. And the reason it's a flat disk is because it came with a cross D2 factor. All right, so this is the big broad outline of the proof. I'll say a few words to step 2 at the very end. For now, I'd like to give you an outline of what's going on in step 1 of the proof. Okay, so let's do that. Here's what's going on in step 1. I'm trying to tell you how to build a skyscraper. I'm going to do this essentially with a sequence of pictures. So I'm going to start off with my hypothesis in this top left picture. And the first step is I'm going to take every point of intersection of F with itself, this thing that I've circled here, just one for the moment, and I'm going to tube it into this algebraically dual sphere. So what that means is I'm going to take a connected sum of F with this algebraic dual, and I'm going to take that connected sum with respect to an arc that lies on F. Since I'm tubing into a sphere, the topology of F does not change, but what it does do for me is that now the intersections of F are going to be algebraically canceling. So here's what I get in the end. Of course, I'll get more F and G intersections. For example, here are some new green-purple intersections. I just didn't draw that just for the pictures to not look horribly complicated. Okay, so now I've arranged that the self-intersection number of F is canceling. So these new intersection points now come in plus or minus canceling pairs. So that's quite cool. And now the next step is a very nice one. I'm going to do this with a few more details than I will for the other steps. This step says that I can actually, coming from the second picture, I can arrange for the purple and green to be geometrically dual, not just algebraically dual, meaning that they intersect in a single point, like this picture in that bottom there. And in case you're wondering, hey, why can't I just do that all the time? The price is slightly a big one. I'm going to have to move green and purple, and I'm going to gain some more intersections between F and itself and G and itself. Again, I didn't draw this, but so green will have some more intersections than it did in the top picture. So how do we do this? Well, if I look at this top right picture, I see that these extra intersections, the ones that come in plus or minus that are paired up like that, well, they're paired up, so they have Whitney disks that pair them because my ambient manifold is also simply connected at the moment. And so let's call that disk W. And here's what a piece of W will look like. Here's a little strip on that Whitney disk W, and it has green on one side and purple on the other side. Of course, I don't know that W will lie, W I just got somewhere in M, so its interior might have intersections with both green and purple. So here's an intersection with green, and here's an intersection with purple. But what I can do here is I can take that point of intersection and push this towards this green intersection. I can push towards the green side, and this purple intersection, I can move towards the purple side. So I'm doing this little move. Again, I'm doing this in a middle time slice, so you should imagine for yourself what's happening in the adjacent time slices. But when I do this, at the end, I'm going to get a picture like this. So I've moved that single green intersection, has now become two green-green intersections. And that single purple intersection that used to be over there has now become two purple-purple intersections. But what I've done now is the interior of this Whitney disk W no longer intersects green nor purple. It may intersect itself, but it's now in the complement of green and purple. And so I can now perform a Whitney move using this immersed Whitney disk, let's say on F. And when I do that, just like any old Whitney move, this removes those two extra points of intersection between green and purple. But of course, I had to pay that price. I had to pay the price of these extra green and blue, purple intersections. But now I've managed to get a picture like this, where the purple sphere intersects the green disk precisely once. You will see in a second why that's important, where that comes up. Okay, so now I'm in this bottom right picture. What am I going to do next? Just like before, where I did this tubing, I'm going to do some more tubing, but now I'm going to tube green to itself. So I have these extra intersection points plus and minus of green, and I'm going to self-tube green to itself along this half of a Whitney circle, so a Whitney arc. And now I'm adding a tube to a disk, so I've made for myself a surface instead of a disk. So that's what that tube looks like. And then, so what I've done, my disk has now been improved to the surface, this bottom stage here. Again, I haven't changed anything on the boundary, so the boundary remains the same. Now I claim I actually get caps for that surface. So where are those caps going to come from? Well, this tube that I added, it has a cap, which is the meridian for that tube that I used. And that meridian intersects the green surface precisely once. I don't want my cap to intersect the surface, so I'm going to take that point of intersection and tube it into this purple guy that I have to help me. And so by doing this process, what I've created is I've created a cap for my surface whose interior lies in the complement of green. There are cap and purple intersections that I have not pictured. And then similarly, another cap comes from the fact that these points of intersection that I've paired, they were algebraically canceling. So there's a Whitney disk for that Whitney circle. The Whitney disk can also intersect my green surface now, but then whenever I see an intersection, I can just tube down into this algebraically dual sphere and get rid of them. And so at the end of this process, I get for myself a picture like this one on the bottom left, where I have a capped surface. There are potential intersections of the caps with each other and the caps with the purple sphere, but the interiors of the caps don't intersect the base surface. And so here you can see how we use the fact that this dual sphere intersects the disk in precisely one point. That was important. And now I'm going to do the same thing again. These caps have algebraically canceling intersections. You can check this. And so we tube those caps to themselves. And then just like before, these become surfaces. So that will become a surface. And then this will also become a surface. And then just like last time, these surfaces will have caps, again, coming from these meridional disks and coming from the Whitney disks for these Whitney arcs along which we tubed. So this creature looks really weird, so I want to spend some time to give it a name. So that's what we'll do next. So these objects are called gropes and capped gropes. So what are those? So a grope of height 1 is simply a compact surface. I've drawn a genus 1 here just for convenience. So the genus in this entire slide can be quite arbitrary as long as it's finite. So a grope of height 1 is just any old compact surface. And a grope of height 2 is built by taking a symplectic basis of curves, meridian and longitude of this base surface, and then adding on other surfaces so that they have boundary there. So I'm going to add a surface like this and a surface like this. So when I do that, I'm going to get something that's a grope of height 2. Then I don't need to stop there. I could take a symplectic basis for curves for these second layer surfaces, and I can add on 4 copies of surfaces to cap those off, and I would get a grope of height 3. So inductively, you now know how to build gropes of any height. And then I don't have to stop there. I can take a symplectic basis of curves for the top layer of surfaces, whatever that is, and I can glue onto those some disks with self-intersections. I don't know how many I need, but however many curves there are in my symplectic basis, I just cap them all off with this. So this should strike you as being slightly familiar. This object is called the capped grope of height n. N is the number of surfaces that I've used. And note, you've seen these before, a capped surface is just a capped grope of height 1. And then another remark I want to make is that I want to really think about these as 4-dimensional spaces, not just these 2-dimensional complexes. And so that by that I mean that this base layer surface, it really is thickened. So I should really think of that as the product with D2. And all of these attachments, these are happening using some prescribed framings to make sure that we can always take some push-offs in a nice way. As always, I'm going to avoid talking about framings in any precise manner, but there will be references again in the type lecture notes. All right, so these are these objects that are called gropes and capped gropes. And returning to our outline of the proof, this is what we have so far. We started with our hypothesis on the left-hand side. And at the end of what we talked about so far, we have built for ourselves a capped grope of height 2. And it's equipped with this nice sphere that intersects it algebraically once, and it has trivial self-intersection number. Okay, so that's where we were at. Now I'm going to get sketchier and sketchier. So first, there's this process, which is called grope height raising. There will be an exercise about this in the type lecture notes, but I'm not going to go into this in great detail. What this is saying is if you have a height 2 capped grope, you can grow the height of that grope to get for yourself a capped grope of height n for any n. It's very annoying to draw, so I didn't draw it. So here's the box contains it, and the top layer of caps, I've drawn them up at the end. So they don't need, these are just portions of the caps that are just sticking out because I'm going to use them. So there's, for any n arbitrarily large, grope height raising produces for you something like this. But again, notice that the boundary did not change. All of that stayed the same. and also this sphere is still around. But all of this is entirely geometric, which you'll also see in the exercise when you do it. The next step is an important one. I have these little discs sticking out. Notice that each of them has something called a double point loop. Namely, I start at that point of intersection, go out along one sheet, come back along the other. That's some loop. And because my ambient space is simply connected, these curves are all null homotopic, so they bound these disks. These disks are totally, I can make them immersed, but they intersect everything that's in the picture generically. But here's another place where my sphere, this purple sphere, is going to help me. Whenever I see an intersection between this red disk and anything that I've already built, I can just push down those intersections down to the bottom and then tube into this sphere again. And then I can get rid of all my intersections by doing this. But notice now my red guy intersects these purple spheres totally arbitrarily. I have no control over that anymore. But what I have done now is I've built for you something that looks like this. So this is, again, with the same boundary. Here's a capped grope. And then at the top of the capped grope, I have this extra layer of dudes that I've put on there. These are immersed disks with a nice neighborhood. They're plumbed disks, if that means anything to you. And what I know is that these caps, they no longer intersect the green stuff. So the red and green, apologies if you're red-green colorblind, is this top layer of disks does not intersect any of the stuff that came before it. And then this purple thing, I've kind of used it up, so I stopped drawing it. And then something even more abstract, which I'm not at all going to go into, says that if your height of this capped grope is bigger than or equal to 4, then you can build for yourself a skyscraper again with the same boundary. None of the boundary has changed in anything that we've done so far. And so here, that finishes our outline of how to build a skyscraper, coming from the beginning, the hypotheses of the disk embedding theorem, and ending up with a skyscraper with the same boundary as what I started off with. So that is the rough outline of step 1 of the proof. At some point, perhaps in the very end of the lecture series, I'll come back to comment on specific parts of this. And then to finish off this video, I wanted to say a little bit about step 2. So step 2 is again, like I said, the big insight of Mike Friedman. And the theorem says that every skyscraper is homeomorphic to D2 cross D2 relative to its attaching region, boundary D2 cross D2. In this slightly more general formulation, this was also due to Friedman and Quinn in 1990 in their book. So I want to say a little bit about what goes into this proof. Specifically, I just want to list some ingredients for you. The first ingredient is, well, Kirby diagrams. So knowing how to represent these spaces, all of these really weird looking spaces like gropes and capped gropes with disks attached to them, what have you, knowing how to express them as Kirby diagrams is extremely useful. So I hope this is kind of motivating to you, like if you already know a lot about Kirby diagrams, perhaps, or you're learning about them right now, that extremely smooth technology is useful for this topological thing as well. It's quite cool, actually. The second ingredient is something called decomposition space theory. This is something that comes from sort of a very pure point set topology side of the world. And let me give you the main question that decomposition space theory seeks to answer. It says, suppose you have a metric space X, it's just some metric space, and I want to take a collection of subsets, pairwise disjoint subsets of X, which are A1, A2, potentially infinitely many subsets. And the question that decomposition space theory asks is, what if I take all of these subsets and I crush them to individual points, like A1 becomes 1 point, A2 becomes 1 point, and so forth. And so that gives me some quotient, a decomposition space of X. A here is called the decomposition. And so this thing is called the decomposition space. When is that quotient homeomorphic to that original metric space that I started off with? Turns out to be a super interesting, very detailed, very intricate set of mathematics that we can talk about, which gives you precise conditions under which this homeomorphism exists. And that is the purview of this field of decomposition space theory. It's very much outside the scope of this course, but there's a lot of wonderful machinery out there about this, and I'll put some resources, I'll link some references for this in the type lecture notes. All right, so that is the end of this line of the proof of the disk embedding theorem in this preliminary form. In the coming lectures, in the live lectures, I'm going to give you many more applications of the disk embedding theorem, a much more general form about the disk embedding theorem, and various open questions that remain about the disk embedding theorem. Okay, so more on that when we see ourselves again next time in the live lectures. See you then.